You know, when you build traditional software, there is this comforting expectation of absolute precision.
Right.
It is like civil engineering. You build a bridge, you follow the blueprints, and the bridge just stands there. It does exactly what it was coded to do forever.
It is deterministic. I mean, it is a completely static system where input A always equals output B.
Exactly. But you step into the world of agentic AI, and suddenly that bridge is analyzing its own load capacity.
Right.
It is redesigning its suspension cables and, 3D printing new supports while the cars are actively driving over it.
Yeah, that is a great way to put it.
We're looking at a computational landscape that is entirely dynamic now. And frankly, for you, the data scientist trying to keep up with this is a little bit wild.
It is the absolute definition of an engineering paradigm shift. We have permanently moved from building isolated tools to deploying persistent actors.
Welcome to the deep dive. So over the last 2 weeks alone, between May 23 and June 6, 2026, we have seen this explosive shift in machine learning.
A massive wave.
Yeah. And today, we are going to cut through the noise of the LMSYS and Hugging Face repositories. We are going to unpack corporate updates from DeepMind, Meta, and NVIDIA.
And we are pulling strategic insights from McKinsey and the South China Morning Post, too.
Right. We are not just going to list what happened, though. We are going to tear down the architecture and understand how these systems actually work.
Because the focus today is strictly on the frontier. We are examining the architecture of persistent agentic AI.
And the infrastructure breakthroughs, right? The stuff preventing these heavy models from completely bankrupting our compute resources.
Exactly. And then the reality of how these agents are already rewriting the rules of applied machine learning in the real world right now.
So let's start right at that frontier. The era of the single prompt chatbot is, it is officially over.
Yeah, completely.
We are now dealing with autonomous agents. Like Google DeepMind just dropped Gemini 3.5, which they are explicitly billing as frontier intelligence with action.
Right, alongside Antigravity 2.0, which is their agentic development platform.
And over at NVIDIA, they launched Nemotron 3 Ultra. That is a model built specifically for long-running autonomous workflows.
With day zero support on the SGLang framework, which is huge.
It is. But the moment you have an agent running persistently over days or weeks, you hit this massive engineering wall.
The memory problem.
Yes.
When an agent is making continuous decisions, observing outcomes, planning subsequent steps, the standard approach has always been to just keep appending that text to the context window.
Right, just stuffing the prompts.
Exactly. But even if you have a massive, say, 2 million token context limit, you run into severe attention degradation.
Right, because of the softmax function in the attention mechanism. If you just keep dumping thousands of tokens into the context, the denominator in that equation gets so large.
It blows up.
Yeah, and the probability scores for any individual piece of crucial information just wash out. The model loses the signal in the noise.
That is exactly it.
Standard context windows are essentially goldfish memory. You fill the bowl, dump it out, and start over.
Which is why the solution emerging in these new papers is fundamentally different. Models like Menzier and Token Miser abandon the linear context window entirely.
Wait, entirely? So what are they using?
They use graph-structured session memory.
Okay, so instead of a scrolling transcript of everything the agent has ever done, it is building like a highly organized filing cabinet.
Yeah, think of it as a dynamic knowledge graph. As the agent interacts with its environment, Menzier extracts entities, relationships, and temporal events from the data stream.
And then it just maps them.
Right. It consolidates those into discrete nodes on a graph. So when the agent faces a new problem, it does not reread its entire history. It queries the graph and retrieves only the highly relevant nodes.
Oh, wow. And we also have the EverMemoS paper, right? Which takes this concept and effectively turns it into a dedicated operating system just for memory management.
Yeah, EverMemo is wild. It processes a continuous dialogue stream into structured memory cells and localized scenes.
And it does this autonomously.
Completely. The architecture is fascinating because it categorizes information based on its utility. It handles plaintext episodic memory, activation-based semantic memory, and parameter-level procedural memory entirely differently.
So it self-organizes.
Exactly. The agent knows exactly where to look for historical context without having to reprocess tens of thousands of raw tokens through its forward path.
Okay, I have to challenge this setup for a second. Let me put my data scientist hat back on.
Go for it.
If we're replacing a simple text buffer with a complex self-organizing graph database, and we are constantly updating state vectors across multiple autonomous agents, the compute required just to manage the memory is going to be staggering.
Oh,
The
absolutely.
KV cache footprint alone, constantly fetching and updating these states, would obliterate the VRAM on any standard cluster. We're going to hit a compute and latency wall instantly.
Well, that compute wall is the exact bottleneck the research community has been targeting. The infrastructure optimizations released over the past 2 weeks are designed specifically to bypass it.
Because you cannot scale agents if you cannot afford the inference.
Exactly.
So, to mitigate a KV cache explosion, my first instinct is aggressive quantization. Just drop the bit precision of the cache to save memory.
Right, but historically, if you do that during a long, complex reasoning task, you hit a snag.
The outliers.
Yes, the outliers in the activation channels completely destroy the signal. You get massive error accumulation, and the agent just starts hallucinating.
And the traditional fix was to use calibration datasets, right? To clip those outliers before quantization.
Right, but as soon as an agent encounters a novel out-of-distribution environment, that brittle calibration fails. Which brings us to a standout paper from this cycle, KVAR-in.
KVAR-in. That stands for Variance Normalized KV Cache Quantization.
Yes. It solves this error accumulation purely mathematically without needing any calibration data at all.
And the paper highlights Hadamard rotation. So let's demystify that for everyone listening. How does Hadamard rotation actually solve the outlier problem?
So it modifies the geometry of the activation matrices. By applying a Hadamard transformation, it takes the extreme energy concentrated in a few outlier dimensions.
The spikes.
Right, the spikes. And it mathematically disperses that energy evenly across all dimensions of the tensor.
Think of it like a live audio mixing board. If you have a track with one massive, deafening snare drum spike that keeps clipping your output.
Yeah, that is a great analogy.
Hadamard rotation is like a plug-in that takes the energy of that single spike and spreads it evenly across all your audio channels. Suddenly there is no clipping. You have smoothed the data out.
Perfect. And once you smooth the data, KVAR-in applies a dual scaling variance normalization.
So you can quantize it.
Exactly. You can now aggressively quantize the KV cache down to incredibly low precision, like 2-bit or 4-bit, without losing the reasoning capability of the agent. It fundamentally changes the economics of deploying long horizon models.
Wow. And we are also seeing optimization on the serving side, specifically for vision language models or VLMs.
Oh, the SGLang update.
Right. The SGLang framework just introduced heterogeneous CPU plus GPU EPD disaggregation.
EPD stands for encoder prefill decode.
Yeah. So in a multimodal agent, the vision encoding phase is highly parallel but incredibly compute intensive. Meanwhile, the autoregressive decoding phase is bound by memory bandwidth.
And traditionally, we force the GPU to handle both phases sequentially.
Which is wildly inefficient.
It is a terrible waste of specialized hardware. The GPU would grind through the massive visual data, then switch contexts to generate text.
So imagine a high-end commercial kitchen. The CPUs are the sous chefs. They do all the tedious, heavy prep work, chopping vegetables, making stocks.
Right.
In our model, that prep work is the vision encoding. EPD disaggregation lets the CPUs handle that massive pre-processing load and then pass the refined data over to the expensive GPU, who acts as the head chef.
I like that. The head chef just focuses on the hard stuff.
Exactly. The GPU is now entirely freed up to focus on the complex, delicate cooking, the actual decoding and reasoning.
By offloading the vision encoding to CPUs, which are vastly cheaper and easier to scale, you reserve your highly constrained GPU memory strictly for the autoregressive generation.
And the throughput gains on SGLang using this method are just massive.
You really are. And we have to acknowledge the global hardware race driving this kind of optimization.
Right, like DeepSeek. They just raised a $6.9 billion funding round, as reported by Pandaily and the South China Morning Post.
Yeah, that is huge capital.
And they are training and refining their massive DeepSeek V4 model utilizing domestic Huawei chips, which is interesting from an objective standpoint.
Right. When you operate under strict hardware constraints or face geopolitical limits on silicon procurement, you are forced to innovate aggressively on the algorithmic side.
So it is driving efficiency.
Exactly. The fact that DeepSeek can train a frontier-class model efficiently without relying on the latest generation global GPUs proves that these inference and training optimizations are incredibly potent.
Okay, so we have graph-based memory giving agents persistence. And we have KVAR-in and EPD disaggregation, keeping the compute costs from spiraling out of control. But now we hit the evaluation problem.
The benchmarks.
Yeah, if I build an agent designed to navigate an enterprise cloud system, how do I actually train and test it? Standard benchmarks like MMLU are static text tests.
Which is completely useless for evaluating an agent that needs to observe, plan, and act in a continuous loop.
Right. You cannot train an embodied or agentic AI on multiple choice questions.
You have to build simulated realities. You need a world model.
A world model. So it simulates the physics, logic, and visual dynamics of a specific environment.
Exactly. So the agent can safely learn through trial and error. And we saw two major breakthroughs here. NVIDIA introduced Cosmos 3, which is an omnimodal world model for physical AI.
They use a unified mixture of transformers architecture, right? We hear the term multimodal a lot, where different models are stitched together, but omnimodal implies a single latent space.
Yeah. A unified mixture of transformers means the model does not have separate, siloed encoders for video, text, and robotic actuation.
It does it all at once.
Yes. It processes and generates all those data types simultaneously within the same architecture. It learns how a text command correlates to a physical robotic movement and the resulting visual change in the environment.
That is incredible. And we also saw EvoPhys-World out of Peking University. They bill it as the world's first human-centric, scene-level 5D world model.
5D is an interesting way to frame it.
Right. I understand 3D space and the fourth dimension of time, but the fifth dimension here refers to human interaction skates.
Traditional reinforcement learning required engineers to hard-code the physics of an environment. But EvoPhys-World and Cosmos 3 learn the dynamics directly from raw spatial and video data.
So it intuitively understands the scene.
Exactly. If an agent proposes an action like pick up the glass, the world model instantly predicts and generates the future state of the environment, including the physics of the glass and how a human in the scene might react.
It is a closed-loop training ground.
Yes, and this fundamentally changes our evaluation metrics.
We are no longer asking AI to answer a question. We are asking it to survive and execute a mission within a dynamic simulation.
Which is why we are seeing a new wave of dynamic benchmarks. Mobile Gym is a prime example of this.
Mobile Gym. That is the highly parallel simulation platform designed purely for mobile GUI agent research, right?
Right. Researchers can throw an agent into a simulated mobile OS and say, navigate to the travel app, find a flight under $400, and book it.
And Mobile Gym tests if the agent can tap the right buttons, scroll, recover from errors, and actually maintain its goal over dozens of steps.
Exactly. We are also seeing OVO S-Bench.
What does that one do?
It tests streaming a spatial intelligence in multimodal models. It forces the model to maintain temporal and spatial awareness over a continuous, endless stream of visual data.
Oh, like object permanence.
Yes. If an agent walks into a room, sees a set of keys on a table, leaves the room, and comes back 10 minutes later, OVO S-Bench evaluates whether the agent remembers where those keys are.
Because traditional benchmarks cannot measure that kind of continuous stateful execution.
Not at all.
Okay, so we have optimized the hardware, built the memory graphs, and trained them in 5D simulations. Now, what happens when these autonomous agents are deployed into enterprise and scientific workflows?
This is where it gets real.
The applied machine learning developments from the past 2 weeks are not just incremental updates. They are structural changes to how research is done. Let's look at the scientific sector.
Google DeepMind just rolled out Gemini for Science, alongside a multi-agent framework called Co-Scientist.
And we are moving way beyond AI as a glorified search engine that just retrieves literature.
Oh, absolutely. Co-Scientist actually proposes novel hypotheses, designs the experimental protocols, and analyzes the resulting data autonomously.
And the success metrics coming out are staggering. Like Molecule Mind released data on their MMID design platform. They're reporting an over 90% success rate in AI-powered de novo nanobody design.
They are literally generating highly specific biological therapeutics from scratch.
The implications of that are profound, and we are already seeing it move from the digital realm to physical medicine.
Right. The South China Morning Post reported that the world's first AI-designed universal vaccine has officially entered human trials.
Human trials, already. That moves incredibly fast.
It does. It is wild. This is an experimental vaccine intended to target a broad spectrum of viruses, including the families behind SARS, MERS, and COVID-19.
And the AI designed it.
Yeah. What the AI accomplished here is a matter of scale. It optimized the antigen design by analyzing mutation patterns across multiple viral families simultaneously.
Which is a multidimensional optimization problem that human researchers simply do not have the cognitive bandwidth or time to compute manually.
Exactly. The agent acts as a brute force intelligence multiplier.
And we're seeing the exact same paradigm in pure mathematics. A team at Princeton published a paper on Goedel-Architect.
Oh, that paper is fascinating.
Right. It is an agent framework powered by DeepSeek V4 focused entirely on formal theorem proving, and they achieved a 500x cost advantage over existing systems.
Which is huge, because formal theorem proving is notoriously difficult for AI.
Right.
Unlike writing a Python script where there are many ways to get a working function, a mathematical proof has an infinite search space but requires absolute logical rigidity.
So how does Goedel-Architect solve it?
It uses blueprint generation and refinement. It does not just guess the proof, it drafts a high-level logical blueprint.
Oh, I see.
And then the agent iteratively verifies its own logical steps against formal languages like Lean4 or Coq.
And with a 500x cost reduction, that means we can now deploy autonomous agents at scale to verify complex cryptography, aerospace software, and new mathematical models economically.
Precisely. And this same autonomous deployment is sweeping through the enterprise sector too.
Right. NVIDIA announced Nemotron, which is a framework helping industrial software leaders build secure, autonomous AI engineers.
And McKinsey just released a really comprehensive analysis on how agentic AI is overhauling legacy business processes.
The McKinsey report specifically highlights B2B pricing. Instead of static pricing tiers, agents are dynamically negotiating and optimizing enterprise contracts in real time based on market conditions.
Yeah, that is a huge shift for finance.
They also noted automakers using agentic workflows to ingest massive, unstructured lakes of telemetry and repair data.
To find anomalies.
Exactly. The agents detect warranty risks and safety anomalies months before human analysts would ever spot the trend.
So the through line here is undeniable. We finally have world models to understand complex environments. We have graph-based memory for long horizon context.
Right.
And we have the KVRN and EPD optimizations to make the compute viable. When you combine all of those, AI stops being a software tool and it genuinely becomes an autonomous colleague.
It is the perfect storm of architecture and infrastructure. Let's recap the journey we just took. We started by tearing down the agentic shift, seeing how models are abandoning goldfish memory for structured, self-organizing graphs like MEMI and EverMemes.
Yeah.
We explored how the industry is sidestepping the compute wall through brilliant mathematics, using Hadamard rotation and KVRN to aggressively quantize the cache, and utilizing EPD disaggregation to offload vision encoding to CPUs.
And from there, we looked at how these models learn not from text tests, but from 5D simulated realities like Cosmos 3 and EvoPhys-World.
And finally, we saw the culmination of all this technology in the real world. AI designing universal vaccines, proving theorems, and autonomously managing industrial supply chains.
It is a totally new era.
Which brings me to a final provocative thought for you to mull over.
Okay.
We are looking at a landscape where agentic systems are writing their own code context files. They are managing their own semantic memory graphs. They are running their own mathematical proofs and designing their own nanobodies.
Yeah, they're doing the work.
So if the AI is doing the heavy lifting of the actual data science and engineering, what is your future role in this industry?
You know, you really have to rethink your entire value proposition.
Exactly. If you manage a team of 5 autonomous agents, your job is no longer tuning weights, cleaning data sets, or writing the pipeline code. You essentially become an organizational psychologist.
Wow.
Or a strategic manager for a network of digital employees. Your daily tasks shift to ensuring their alignment, auditing their memory structures, and resolving conflicts when your agents disagree on an experimental protocol.
You transition from being the builder of the bridge to being the mayor of the city.
Oh, I love that. Think back to our opening metaphor. The bridge is now building and repairing itself. The suspension cables are autonomously adjusting to the traffic.
Right.
As a data scientist, you are no longer pouring the concrete. Your job is to stand back, observe the entire dynamic system, and guide its ultimate purpose.
It is a wildly different job description than it was even 2 years ago.
It really is. But honestly, it has never been more exciting. Thank you for taking this deep dive with us. We'll see you next time.